All right. Well, welcome everybody to today's Lunch and Learn. I am Shelley Granager, Director of Alumni Relations here at CARA, the Center for Alumni Relations and Advancement. Before we start today, I just want to take care of a few housekeeping items. We are recording today's Zoom, and it's going to be uploaded to our CARA YouTube channel. This does take a couple days, so maybe look for it on Monday or Tuesday next week. But feel free to share this with others that you think would like to hear about the research that's happening inside of our Materials and Metallurgical Engineering department. I encourage you guys to use the chat function below to say hi to everybody. Let us know who's here, your major, your graduation, or if you're from a department, let us know what department you're from. To use the chat function, click on that word bubble at the bottom of your screen and a chat window will pop up. Please switch your responses to all attendees so we can all see what you have to say. If you have questions for Dr. Donovan today, enter those in that Q&A section, and then at the end of her presentation, she will answer those for you. I'm going to start off the chat function with my email address. I would love to hear from you. I want to hear all sorts of things like what you would like to see for your next Lunch and Learn, departments that you want to hear updates from, and if you would even just be interested in a alumni event in your area. If you're interested in hosting or participating in that, I'd love to help you get that going. So please reach out anytime. All right, so it is my pleasure today to introduce Dr. Donovan. Dr. Katrina Donovan received her Bachelor's of Science in Chemistry from South Dakota School of Mines and Technology in 2010. She earned her master's degree in chemistry at San Jose State University in 2014. And then she went on and graduated from Oregon State University with her PhD in materials sciences in 2019. As a 3D printing intern at Hewitt Packard Inc. in Corvallis, Oregon, she studied fluid flow through porous polymer media and contributed to 3 patents. Sorry if I mispronounced those, Dr. Donovan. She became a research scientist with Dragon Materials LLC in Rapid City, South Dakota in 2018. In 2019, she became a lecturer in the Department of Materials and Metallurgical Engineering at South Dakota Mines. Dr. Donovan balances motherhood with teaching and research, as well as the STEM outreach and undergraduate mentorship. She was awarded the 2020 Outstanding Recent Graduate Award at South Dakota Mines, partly due to her outreach. So with all of that, I would like to welcome Dr. Donovan.
Thank you, Shelley. I appreciate it. And hopefully everyone can see my slides now, hopefully.
Yes.
Okay, sounds good. So thank you for the introduction. The title of the talk was Research in the Materials and Metallurgical Engineering Engineering Department. I will say I cannot cover our entire department here in that talk, so I'm just going to focus on one of the programs that we have, which is one I've been a part of this past year. Actually, we just entered our first year into the program, and that's the National Science Foundation grant that we got for improving undergraduate education, STEM education, and we've titled it Art and Engineering Program. So I'm really going to focus on the research that's come out of this grant. So just a little bit about metallurgical engineering. Some of you may have seen this slide before. It's one of the few Bachelor's in Science Metallurgical Engineering degree programs that are in the US. Kind of our 4 main focus, or really 5 main focus areas, are mineral processing and metal extraction. We can see that on the far left. We have metal production, so casting, that type processing. We can see that here. And then properties and performance. And then on the bottom is the very important part, which I'll actually be covering today, which is the recycling and sustainability. So we kind of have a full loop here. Today, though, I'll really be focusing on some recycling, mineral processing, and then actually just processing as well. But here's kind of just a big picture of what we do in the metallurgical engineering department. Just a little background on the metallurgical program and really how we started this art and engineering program within the department. So the program has a history of incorporating hands-on. We can see a student on the right-hand side, blacksmithing. We have a team of blacksmithers on the bottom right-hand side. They competed in the TMS international conference that's usually hosted every year, but our team our School of Mines blacksmithing team actually won that year. This year they got second. So good history of success, both with the program and competing. So we've really got these hands-on groups that like getting their hands dirty. And so what we've seen is there's a lot of kinesthetic learning that happens with this. It's fun, but it's also a lot of learning that happens. So what we've seen is these activities have strengthened student understanding of metal processing and the structure concepts. So to be able to make a high quality sword that would stand up to these competitions, they really had to have a very fundamental understanding of metal processing. So one of the things we also saw with this is as we began to expand the blacksmithing and have more of these club opportunities for students, it increased our enrollment. So that was something we wanted to pursue again, but from a different perspective, not blacksmithing, but this artistic perspective. Also with the blacksmithing that we saw was we had multiple local artists that would come in. So when I say local artists, I mean blacksmiths that would come in, interact with the students, and they have years and years of knowledge. So it was awesome to see them integrating with the students. And so with 10 plus years of this, seeing this evolve, we began this process for the art and engineering with the research hypothesis of, can we integrate artistic components into the curriculum to increase innovation? Because really what we want is creative and innovative students. I want them to be able to go out into the workforce, and we follow the processes, but still be able to think out of the box when we need to. Given COVID, the last couple of years, we really had to have some of these out of the box and innovative ideas. And that's really what we're pursuing with this art and engineering program. So the concept is to integrate art into the metallurgical engineering program while reinforcing science and engineering concepts. If you guys are watching, I do have the QR code for the website. We're still building it, but you can see a lot of what we've done with this program already. And then our logo is up on the right-hand side. So if you see that around campus, you'll know that's us. But the big, goals from this was creativity, innovation. When you're working in, a blacksmithing situation, for example, you got to be collegial, being respectful of where a hot metal is. There's a lot of creative or entrepreneurial ideas that come out of this as well. And then since we are an undergraduate program, focusing on that student retention is really important. We've seen historically with the blacksmithing, both an increase in numbers, but also good retention as well. Obviously, the overall or big goal of this is the high quality engineering that graduate from here. So with that in mind, we received funding in October of 2021. So our first official semester of integrating this program into our curriculum began spring of 2022. And so we started by handing the junior design team 5 buckets of minerals and telling them process process a creative aesthetic piece. And so they had these 5 buckets. They had to look at all the minerals in them and see how can they combine them to make an aesthetic product. So as it says here, each team was tasked with a common design project, but they had to bring their own creative piece. And I'll walk through some of the pieces they had. So we can see Grubby here. It was a complex project with aesthetic challenges. Grubby's got a hat. There's all these overlips and challenges to slip casting something like this. And the cool thing about this is the juniors came with a lot of mineral processing interest and background. And it was interesting because we had one group that was going to do this, and we had an artist who worked along with us. And at one point she looked at the Grubby and she goes, "Oh, this is going to be really tough. I'm not sure if we can do this." And it was pretty awesome to see by the end of the term, and you can see the Grubby in the center. She was like, "That was amazing." She's like, "I didn't know that they could do that." And it was cool at that point when I realized what we were doing, because the artist was skeptical about what could be done. And I think it was cool for her to see, what the engineering students can really bring to it. So this one was super cool because just the challenges of how complex Grubby's shape is, they were able to really create a cool product with that. The next one is a teacup you see here, and the group did get to drink the tea from the teacup. But the cool thing they did is they did a single fire, and I can kind of walk you through what that means. When you have a clay body, it's in a green state. And so it's you can think of it simply as like a mud. It's, it needs to dry, but we have to fire it so it becomes a solid piece. And so it goes from a green state to that fired state. And this is what it looks like fired. Then they glazed it. And this is actually acrylic paint. They really did that. But there's some glazed scrubbies in our building. But that's what it looks like after. So fired, glazed. What they did, so it requires 2 fires to get to what they did. This group, theirs was interesting because they skipped that first fire and did a fire and then painted it with a glaze. And then they didn't do that fire. So it cut out a whole day of firing, which is really interesting from an engineering perspective, because obviously if we can do something in 1 step versus 2, it's pretty useful. There was a couple other teams. So each team, as I said, brought that uniqueness. Dr. West, our department head, he got his mug on a mug. The rest of us weren't so fortunate, but he has a mug of himself in our display case. It was pretty cool. The students had asked to scan his head. In this group, they 3D scanned his head. They made a mold. They did a slip cast into that. They made their own novel glaze. And this was all with, this was all with clay formulation that they had looked at, they had made. So it was their own novel recipe of clay. So that was pretty cool. Another group did shot glasses. And so they went through a lot of different, they did 3D printing and a lot of different mold designs to be able to make multiple shot glasses. I think they can make, one point they had 6 or 7 molds. So they could get through quite a few shot glasses. And then this last group, which I'll talk about a little bit later, their novel approaches, they had their own clay recipe, but they really were interested in glass glazes. And so they, as part of this art and engineering program, we've really been pursuing glass and integrating that into some of the things. So we've done stained glass modules and some other torch work, but there's all this recycled glass. It's not enough to integrate into something. So it's really just scrap glass. And that's what this group did, is they went and took a lot of that scrap glass and ground it down to a fine powder to then be able to make it to a glaze. So that's just some of the stuff we're doing, but really this junior design was really kind of that first step into more the research side that I'm going to talk about today. It was a really good opportunity to look at things and start asking, as a researcher, asking questions of, all right, we got a product, but how did this work, or why did this work? And that really steps us into the research side of things. And so I'm going to present 2 case studies today. The first case study was some of the leftover materials we had from junior design. I wanted to investigate them a little bit more. And so the first one was to formulate and analyze commercial glaze formulations, because we wanted to eventually do some mineral processing to be formulating our own novel glazes, but we wanted to start with some of the glazes we already had. So Isabel Nielsen, who is a 4th-year student, she's on the left-hand side here. She was an REU, so REU is research experience for undergraduates. She was a student in the Back to the Future program. She worked quite a bit on this. She also was paired with Olivia Grenager, who's in the middle here. And Olivia is an Army AEOP student. She was a high school student. Her and Olivia worked together through a lot of this. That's the first case study. I also have Kieran here. She worked with Dr. Keller. She did a lot with the clay. So some of the clay I talk about, Kieran did a lot of the formulation for that. Case study number 2 is novel clay and glaze formulation. And so we had a ceramic engineering camp, and Jenna Saylor helped a lot with that. And so we're going to be talking about some of the novel clay she did and the glass glaze formulation she did. So some of hers is some of the stuff she learned from junior design and then applied throughout the summer. And so this work she presented at MSNT, and I'll talk about that here in a little bit. So jumping into case study 1, which is the glaze analysis. In general, glazes really have this in the art world, it's very much regarded as an art form, and it's a skill that was passed from master to student throughout the centuries. And the idea of an apprenticeship really is applicable here, because somebody who's using glaze or even making their own clay, they have their special spot where they go out and dig and that's, that's something the master shows the student, and then you have this special spot where you are getting the best clay because you know the secret spot. So it's not something that's always wanted to be shared historically, but it really is this skill, and especially working with a specific type of clay, it behaves a specific way. So both with clay and glazes, getting those formulations, very, very much a lot of art and science. So you can see the beauty. There's a lot of things that's leveraged here. And I think this picture on the bottom right-hand side is kind of one of my favorite. It's actually a picture I took in DC in the art museum, one of the Smithsonian's. What I think is super cool about it is it's a slab build. But what they did is there's holes in here, and as it melted, you get all these cool fluid profiles, and it's all based on the chemistry and viscosity about these materials and the thermodynamics, the temperature and when it melts and stuff. It's a really, really unique piece, but it really, to me, ties both that art and that engineering. So aesthetically beautiful, lot of science that goes into it, and that's, these masters, that was something that was handed down. So glaze fire, I talked kind of a little bit about how we have a first fire and then a glaze fire. The glaze fire, we typically see that being a little higher temperature than a bisque, or what they call a first fire. And so glazes tend to consist of things like silica, alumina, and metal components. In silica and alumina, the ratios of those dictate the temperatures we go to, and the different metal components, specifically like the transition metals, those are what give us our colors at these high temperatures. And when I say high temperatures, we're pushing 1,000, above 1,000 degrees Celsius for the most part for a lot of glazes. Another thing about the glazes is they really are a glass. It's a very glassy surface. We're heating them up so high, they're in a glass state. So and they cover the surface. The other thing that was interesting with junior design, we had some groups doing impact testing where they're just dropping them. It's a much improved impact when you start glazing. It really gives it a tough outer surface that's good for wear resistance. So for the first one, for this first case study, one of the materials and methods we used is they created a bunch of tiles, and we can see the tiles on the right-hand side here. We had 3 different glazes that were left over. So we had a blue glaze or a navy glaze, this malachite glaze, which was of a lot of interest to us, and then a white. And so the students began just by developing different color combinations. They rolled out test tiles, and then they fired them to cone 06, and that's the artist in that community talks in cones. And so a cone 06 is at about 1,030 degrees Celsius. And then the ramp rates probably look a little interesting. A lot of the ramp rates were developed in Fahrenheit. So 132 seems a little bit odd. It's because of that. We used a couple different clays. The Highland Grog and the white stoneware were both commercial clays that were used. And then a Belfouche shale is a shale that's very common in this area. So it was just literally a clay in our backyard. So it was cool to see kind of the different clays we used and how the colors look differently on them. And then the glaze combinations are malachite, blue, and white, and then a 50-50 of those. And these were commercial commercial glazes that we started with. So the malachite is this interesting color where we've got some green and then some brown with it, and then Old Navy is the blue, and then the snow white at the bottom. So, and these images were done on the white stoneware. So just looking at the different clays and how they appeared, or different glazes on the clays and how they appeared, was where we first wanted to start, because there is an aesthetic component to a glaze. You want it to be aesthetically pleasing, and putting, a glaze on a darker clay versus a lighter clay is going to give you different colors, even if it is the same glaze. And we saw that here from left to right. So here Isabel had added 2 layers of malachite glaze on the left, which is to the Hawthorne Grog. And I will say I think I had a typo on the earlier one, Highland, but it's a Hawthorne Grog. And then on the white stoneware, and then on the Belfouche shale. So we can see slightly different colors looking at it, and we can use an image J to get a mapping of the red, green, blue. So the intensities are about the same for a lot of them, but as you can see in each one, there's its own unique profile. And so just another way to characterize the surface, which is pretty important from an aesthetic side. Also, it'd be interesting too, if you want to know what the clay looks like underneath, just the color. For another layer of characterization, that we did was scanning electron microscopy. And for scanning electron microscopy, what you're doing is very similar to optical microscopy. These images here we're taking on an optical microscope, so we're using light. With a scanning electron microscope, what we're using is an electron beam, so we're essentially shooting electrons on the surface. It gives us much better resolution. We can really zoom in and look at surfaces, and at the bottom you can see some pretty unique surfaces here. These are all the SEM images at the bottom, and so this is our malachite, and we kind of see that from the image here where we see some of this lighter and darker, and we see that we still have a little bit of that going when we mix it with the blue, and still a little bit when we mix it with the white. Another thing that we did as well was X-ray diffraction. For X-ray diffraction, we were really looking for this atomic percent for each of the elements. And what we were looking at here was for color. So we were really focused on, the metals that would bring out some color. So if we look at the malachite, we have about 4.8% titanium and 7.6% zinc. And then we also have the copper here. So very, very high in those values. Apologies. White, we don't see a whole lot, just a little bit of titanium, which isn't super surprising. And then for the Navy, we see a lot of that cobalt, which is a pretty typical metal used to get to blue. So, and then for the 50/50s, we kind of see those blend. But the big thing we want to kind of look at is this malachite, and that was of interest to us. The other thing I should mention is you can get some atomic or elemental data from a scanning electron microscope if you hook it up to an EDS, and I think I have some data later. For this one, we didn't though, because we wanted high quality images, so they were carbon coded. That way we didn't have a charge buildup. When that happens, it blurs the images. So all of these were carbon coded at the bottom. So this data you're seeing here for the atomic percents came from an XRD. Another thing we really wanted to do is we really wanted to start to look at the malachite. And so what we can do in the SEM is we can zoom in on a region and get that elemental data that I had talked about. So this data is from the EDS, and what we did is we looked at all of it. We did a mapping on all of it, but then you can also take a point. So you see point 1 and 2, take a single point and look at it. So we see, I apologize because I'm trying to use my thing, it zips, but you can see this long rod and hopefully number 1 here. So just looking at point 1, we see this long rod. So what we see with that when we look at point 1 over here is there's a lot of titanium in that. So titanium is probably growing these long rods. We see some silica in it as well. And then if we take a look at point 2, which is this white looking crystal here, we take a look at that and we see quite a bit of titanium there, some zinc and some copper. So kind of seeing some of the colors we're seeing and why we get those, and the shapes from these particles and the rods that are forming are due to the different elements and the crystal structures that are formed. Overall, though, what we'd expect is a lot of alumina and a lot of silica, especially a lot of silica in this case. And we see that. So for the overall map of this entire image, a majority of it, this blue here, is silica, which is what we'd expect for a glaze. But it was really interesting for the student to go in and identify the different features. The little circles you're seeing, or even some of the bigger circles, those are bubbles and escaped gas that you'll see. And that's, at least from the glazes I've seen so far, that's pretty common to see some of these air bubbles. I mean, you got to remember, we're zoomed in. I mean, here you're seeing 50 microns. So some of these bubbles are pretty small, and some of these pieces are a little bit bigger, 20 to 25 microns for some of these. But we're zoomed in quite a ways for this. So just kind of a big wrap up on this student's project and Isabel's project, Isabel and Olivia. So one of the cool things they saw with the red, green, blue profile was on the same glaze, the patterns were pretty similar. The intensities were pretty similar, but the cool thing is you can kind of fingerprint each one and see that it had its own unique profile. We're talking about glazes. We often talk in terms of glass formers and intermediates. So for our glass formers, we see silica and alumina, and sometimes alumina is also in that intermediate. But for the glasses, we saw a couple slides ago, or one slide ago in this case, we really saw a lot of silica here. So that's common. And then elements used for pigments we saw, and I talked about a lot of those. So we did see those in the malachite. And then we also used XRD to confirm with the SEM. So with the EDS data from the SEM. And really, we were just kind of looking to learn a little bit more about malachite and coatings in general. So the second case study, which was Jenna Saylor's, hers focused on both novel clay and glaze, and part of this started in junior design and then continued throughout the summer. She didn't work full-time during the summer. It was kind of a side project for her, but it's been a fun passion project for her, that's for sure. So apologies. The first part was the novel clay. So using native minerals from South Dakota. I kind of, when Jenna had presented this, so I gave a long background about the Black Hills. I'm not going to spend too much time on that, but the Black Hills, there's a lot of different geological, features that are pretty interesting, from Mount Rushmore. I'm showing a lot of granite here. There's mica. One of the clay samples, or one of the samples we got for the junior design, was from some feldspar that was given to us by Pacers. So a lot of different minerals come from the hills and is known, for Black Hills gold. And here I really like this picture because it shows a pretty cool, layout of the geology. So we see the limestone plateau. We see this region here. You see the granite and near Keystone, Harney Peak, that area. So just the nice graph, I think, of what the geology looks like. But we see minerals such as quartz, feldspar, muscovite, and biotite, all found in the granite. And not historically, but geologically, these minerals form from beneath the surface of molten magma, and then we get a lot of cool rocks that come from that. The cool thing about these minerals, quartz, feldspar, muscovite, these are all materials that are used in clay. Quartz is also silica, so we get a lot of that in our glazes. So it's amazing what we have in our backyard that we can be able to work with to make both clay and glazes. So part of this is from junior design, and so their approach was in junior design to create a clay body. And so their approach was they were looking kind of towards the white earthenware. A lot of the clay we had was probably closer to the red clay or the red earthenware. And this is a chart provided by Linda Bloomfield in a really good text if you're interested in any of this. But for the kaolin clays, we see illite, quartz, and iron oxide. Kaolin's like a weathered feldspar, illite's a weathered mica. So with the red earthenware, that's what we see. These can be straight out of the ground with little to no processing, which is nice. I mean, it's cool if you can take a shovel and make this. They did quite a bit of refining in junior design to get to some of the bodies they made, but a lot of it can just be dug out from the earth. And generally the clays are characterized by firing temperature, and we can see 95 to 1150 for a cone 08 to a cone 1. And so the couple things to remember about the clay after that first firing is it remains porous until you glaze, and then higher firing temperatures make it non-porous. So here's some of the buckets we provided for the clay. Whoops, apologies. For the clay they did, they did a lot of Tower Road, which is literally off of Tower Road. This is the Sturgis Road, which is a lot of calcite. And then this bucket is from Pacer, but we had 5 different buckets they could work with, and it shows the breakdown here of the quartz and the kaolinite. Each of the students had an XRD they could work off of, so that XRD provides elemental data as well as mineral data, so they could look at what combinations they would want based off of this type of composition here, where they need china clay, ball clay, feldspar, those types of things. There's Pacer, there was a lot of feldspar in there. So they were given all the elemental information for this, and the composition her group, Jenna's group, had come together with was a 50% Tower Road, 26% Corral Drive, Pacer, and then Sturgis, and then Wharf Mine. So they actually used all 5 of them. And then here's what the weight percent of each of the minerals looked like. And I believe this data they got from their XRF. But what they were shooting for was a white earthenware, and that came from Linda Bloomfield's outlines. That was their approach. For the clay processing, they crushed the minerals using mortar and pestle. They ground it down to a fine particle size using the puck mill. So it was about 74 microns, added the constituents together and mixed while it was still in powder form. And so they had a ratio of 5:1 for their clay powder to water. And their approach was to do pinch pots. So you can see from left to right, their powder, once they added the water, and then they pinched it into a pot. The second part, which we really want to focus on, is the glaze formation. So with a lot of the outreach that's done and some of the labs we do, we end up with quite a bit of scrap glass. In this case, she was focusing on a green, and she mixed a couple different greens to get this. It's, you can sort them into piles, but the other challenge here is not all the greens are going to be the same, especially if you're buying glass from different places. So you're going to get different shades. But here's the green. As I said, this is all stained glass scraps, so it's all recycled, but just mortar and pestle. It was ground down to, they said a reasonable size. They never particle sized it, but at that point, because they did grind it down even further with the puck mill, which is about 74 microns. And then once again, added water, and then they got this kind of paste look here. So that was what they used to apply to the surface. So just quickly kind of looking at the glaze composition. So what they wanted to do was match the glass they found. So there's soda lime glass. They were using stained glass, which is slightly different, but what they thought would be similar to soda lime. It's a little bit hard because we didn't go back and redo this. There's a lot of light elements we're missing here. So you don't see sodium, oxygen, a lot of those, which clearly account for quite a bit here. But we do see a large number of silica, which doesn't surprise us because we see it there with the quartz as well. So we had gone with the assumption, given the light elements, that we probably have something similar to a soda lime glass. And so, which was what we'd expect for a stained glass. So compared, we'll probably go back and redo this because we really want to know what those lighter elements are. We'll probably end up doing XRD on it. But for a first run at it, we know we're pretty close to what we'd expect for the glass. This is a couple examples of colors that we see here. If we want to get a specific color in a glass, so like selenium oxide gives us red. Cobalt oxide, we talked a little bit about that actually with the navy earlier. It gives us a blue or a violet color. So these are the metals you'd put into a clear glass. And using Linda Bloomfield's text, what we followed was this clear glaze here. So it's 20% whiting, which is calcium, feldspar, which we had from Pacer, kaolin's a clay-like, and then silica, which is what our glass will be contributing. So, and you can see here. Then once we want to add color, that's where you'd go for here. For us, the glass is already coming with colors in it, so it already has those metal additives. So kind of just sorting by colors was the approach. So once we had our glass ground, we then started our trials. So we tested different amounts of additives in the frit. So when it hits this powder state about here, it's often called frit. So really, really fine powder. So for the frit, we tested different amounts. So we started with this trial 2, and we really followed what we saw on the previous page, which was the colored glass. If you look here, colored glass is about 25% of it. We got some kaolin, Pacer feldspar, and then we still had Sturgis Road and Tower Road, which are part of those clay bodies. And you can't even really see very well what was in here. It clearly didn't work very well. So then we refined that glaze, and we went to a lot more glass, more kaolin, and just stuck with the Pacer feldspar. And when we did that, we got a little bit more color. You can kind of see it a little bit there. We still weren't quite right. And so we eliminated the feldspar and came down to just colored glass frit and kaolin, and we can see a lot more color in those two. So that was the mixture of glass or frit and kaolin that we chose, because we could actually see the glaze in these cases. We wanted to go even a little bit further and refine it. So we tested different amounts of kaolin and colored frit. So we found that ratio from trial 4, but now we really wanted to dial it in. And we have a couple images here, but what we focused on was the colored frit to kaolin and what it looked like. And you can see here with the blue, it's got a little bit better color just visually with the eye. It also covers the glaze a little, the glaze covers the clay body a little bit better. So that was the one that was chosen just based off of glaze coverage and color intensity. So once we got through knowing our ratios, we then started using a lot of the different glasses that we had recycled. So stained glass scraps were repurposed for use as a ceramic glaze. We started encountering quite a few issues. When you start using a different color of glass, we found a lot of things happening. As you can see, we listed all the challenges we have. Part of, the focus was to use the recycled material. And so we didn't stick to a single color. It was, what do we have available for colors, and kind of sorting it there and trying to work through, because the purpose was really to recycle. And so we didn't stick with a single color. So with each one, it was its own unique problem, from seeing cracking in some of these. One of the glazes, and I can show you back here a little bit, when we use the puck mill, you can see little dark spots here. It wasn't, we're still getting, just because other people use it as well, we're getting some contamination there. So just a lot of things we need to dial in a little bit more. The cool thing is we were able to get some glazes to work with this glass. We still need to, fine tune some of the colors here as well. But it was cool to see that glazes could be made using this recycled glass. So just once we got to a powder frit, we had tried a couple different liquid mixes. So we've used 95% ethanol in powder, and you can see A over here, that was that one. That's A down here is what it looked like when it was fired, just in this crucible. B was just firing it. It was a suggestion that was made, just use your dry, no water, and see what happens, and it should melt. It did not for us in that one, which was interesting. C was a powder mixture and a pre-made clear glaze, so we can see that here. And then D was this water and pre-made glaze in here. And so then you can see, oh, they're flipped here. I should have numbered these, but this here at the top is our is the glaze, the purchased glaze in the glass frit, and then these two, this one is the ethanol, and then this one is the water. So the glaze, the ethanol, and then the water. So I'm actually going to show you what it looked like here in a couple slides under micro CT, but it was cool to see we could at least produce a glaze in all of these cases. Some of them are not the most ideal, but we were able to do so. Glaze application. So once we had those mixes, we applied them to our first fired pottery. So here's a pinch pot. These were nesting bowls. They had been fired at that point to 900 degrees Celsius once the mixture had been painted on. So they'd first been fired, and then they were glazed and fired again. So this is what they looked like after we'd applied it. So just quickly, the other thing we did was, that was for junior design project, but we really did a pretty systematic study of what it looked like when we did little pucks. And so you can kind of see the different pucks we did. So this one is with it was test one, so that's what the T1 is, but it was with the ethanol. And so these pucks are about 1.35 inches. So the glaze coated this pretty nicely. There's some minor cracks there, but overall it was a pretty nice coating. This was the commercial glaze with the glass added, and we got a lot of bubbling, and you can see that here. This is just snapshots from a micro CT. And what micro CT does is it takes like steps through a 3D object. It takes layers and it's images, and then it's put together to video. I'll show you here, but what it does is we can look at the different densities. So black is air. So we can see here, we can visually see here, all these bubbles. That's air that's being trapped in our glaze. And I'm not quite sure why a commercial glaze would have this, bubbles quite like this. These are pretty significant, but we can see our bubbles. This is our glaze. And then this is our clay body. Here we can see this clay body has some pretty big pieces, and you can see it even through the glaze. But clay body, and then we have our glaze on top, which this one looks pretty good. And then we also had water, which it has some air bubbles. We can see a crack right here, and you can look at this and see quite a few cracks. And so the CT really got that. So glaze and our clay once again, and some bubbles, not quite like the the commercial glaze, but still some bubbles. So here's the micro CT. And so the bottom part here is our glaze, the lighter color here. We can see an air bubble there. And then this darker phase here is the clay body. And so you can see what it's doing is just taking steps through the body, through both the glaze here and then the body. So it's pretty cool to see all the different particles. It helps us just look and see how well did we do in terms of grinding particles that were added. I believe these larger chunks we thought ended up being some calcium that we thought we got much smaller. So they tend to be pretty big chunks, but you can see the air bubbles there. We have a small crack there in the glaze. This one is the ethanol one. And so we see some little bubbles here as well. Oops, sorry. Didn't click through correctly. This is the traditional glaze, and this one had some pretty big, as we saw, air bubbles. We also have the scale bar down at the bottom, so 1,000 microns. You can kind of see these are pretty significant air bubbles, and we do have some larger particles there as well. So that was the traditional glaze. And then here's the water one. And so here we can see a pretty significant crack as we're going through it, as it's stepping through it. Another crack. There was quite a few cracks that we saw in the water one, and some pretty big bubbles too. But bubbles like this wouldn't be as noticeable as what we saw on the glaze. But there's quite a bit of cracking that we saw with the water. So just a quick conclusion from this case study was we determined the correct firing temperatures for specific glasses. There were some that were successful. We still have quite a bit to do. We still need to test for a lot of those. And then just continually collecting and recycling glass. One of the cool things is Jenna had recently done a STEM outreach with Rapid City High School. They had some extra stained glass, so we went and did stained glass with them, but any of the scraps were given to her. So she's replenishing her glass storage or her glass cache in this case. So kind of big picture overall conclusions from this is a great preliminary progress, both by high school students and undergraduates. You know, my focus is primarily undergraduates, so it was cool to see Isabel. She presented a poster on her work at the South Dakota Research Symposium. She also did an oral presentation at IASIS, and then Olivia actually had to submit an abstract to Army AOP as her part in this. And then Jenna recently presented just last week at ACERS, which is part of the MS&T, so the Materials Science and Technology. And I probably should have said ACERS is the American Ceramic Society. So she gave a talk there and it was very well received. Additionally, she had submitted some of her work into the ACERS competition and she won. So that was a pretty cool thing to see. And for me, a lot of this happened during the summer. Isabel worked for me during the summer. So I'm looking forward to this upcoming summer when we start making a lot more process on this. Just some acknowledgements. There was a lot of people who helped with this today. Dr. Keller helped a lot with student advising, material supplies, a lot of things. So I really wanted to thank him. Dr. Brett Carlson, he helped lead Jenna's junior design team, so helped with that process. Dr. West helped with financial support. All the awesome micro CTs are from Dr. Cross. There's also a couple different grants that went into this. The big one is that NSF IUS grant, which is the art and engineering grant we have. I had some South Dakota Mines mini grant that I received. Also want to thank the junior design teams. They all helped each other. And then ACERS helped support a lot of Jenna's travel to that conference. So that was all I have. Thank you for your time. Is there any questions?
Sorry, my mouse disappeared on me, so I apologize about that. Thank you, Dr. Donovan. Would you mind stop sharing your screen real quick? And I wonder if I can make her stop sharing her screen.
Awesome.
There we go.
Yeah.
I want to thank everyone for coming. I want to thank you, Dr. Donovan, for your talk. We don't currently have any questions, but I want to give you guys a chance to ask questions. So while we're waiting, while I give you that moment, I wanted to share with you guys some upcoming alumni events that we have in the area, or in the nation, I should say. And I will give you a minute to throw a question in that Q&A section there for Dr. Donovan.
I'm going to make a quick comment. I should have
Yes.
said, I kind of focused on the research. I should have really had shown there was, you wanted me to stop sharing my slides, right?
I did. I stopped you. Yep.
Okay. Oh, fair enough. One of the really cool things we did, I mean, Olivia helped a lot this summer. We actually ran a ceramic engineering camp this summer that went really well. And I think I'd showed a picture of Jenna in a bus with a bunch of students. So that will be something we're going to be offering again in the summer of 2023. So if you know somebody who's interested in anything that I showed today, that would be a really interesting camp for them to attend. So we would also like it helps a lot if the students have had chemistry walking into that, but that is something we're going to be offering summer of 2023. We did it summer of 22 and it was great. So we're going to be doing it again.
I heard good things about it, and I have to put a plug in. When she says Olivia, that's my Olivia. So
Shelly's probably good.
Yes, so it's been fun to see her get to explore different avenues while on campus, which is what makes this campus great, is the opportunities to our students. So even before she got here as a freshman, I really appreciate the time you put into that too, and into her. So thank you for that, Dr. Donovan. While I give you guys a minute to throw in some questions, if you have any, I just want to give you some upcoming alumni events. So we do stuff on campus. We have our digital department updates and our lunch and learns, but we in November have a lot of our, and I have an old one up here. Sorry about that. So I'll just tell you about them. We have in November 2nd, we are in Cedar Rapids, Iowa. In November 3rd, we're in Marshalltown, Iowa. November 5th, we're doing an alumni event in Denver, Colorado. So if you are from that area or have people that you know from that area, invite them to come on out. It's a free night to see Dr. Rankin. It will be at each one of those events, as well as someone from Kara here. Mike Keegan is going to the Iowa events. I will be at the Denver event. And then November 19th, the Sioux Falls area, we will be out there for men's basketball. And so all of those are on our website and coming out with invitations too. So Dr. Donovan, I don't have any questions in here on this. You did such a great job explaining it. So for those of you that had a chance to look at her QR code to see some more and be able to share that, I want to remind everyone that this video is being recorded and we will post it to our Kara YouTube channel. I will also follow up with an email to everyone with a link for that video for everyone that registered and everyone that attended. So I know some people wanted to be here but weren't able to be here. So we want to make sure that they get that information. And I think this is just a fun exploration of how you can take arts into engineering. I know that students have really loved it too. If you out there, you alumni, have some suggestions on things that you would like to see in our Lunch and Learns or digital department updates, reach out to me. Again, my email's in the chat, but it'll also be in that follow-up email I send out to everybody. And again, I want to thank Dr. Donovan so very much for your time and for your passion that you shared with us today. Thank you.
Thanks, Shelly. Have a good day.
Thanks, you all. Have a great day. Bye-bye.